So this is section 7.3. So the process we're going to talk about today for solving three variable systems, the nice thing about it is it's very mechanical. So there's not a lot to it. You just kind of do the same thing over and over again. And it's also easy to generalize to 4 variable systems, 5 variable systems, and into a process that you could actually tell a computer or a calculator how to do. And eventually that's what where we'll be going with all of this stuff. So we're going to talk about the process today. On Friday, when we talked about our 2 variable systems, we said 2 variable system, so something like 3x plus 5y equals 7. If we graph that, we get a line. So we're going to talk about systems that look something like this. I'll write up a system of equations, x minus y plus 2z. And I'll show you what our goal is, and then we'll talk about how we're going to get there. So our goal is to turn a system of three equations, so we'd have x's and y's and z's in all of our equations, into something that looks like this. We call this, when we get it into this form where there's all 3 variables in the first row, 2 variables in the second row, and 1 variable in the last row, and usually we want to get it so that it goes in this stair-step pattern. It's not a requirement, but usually this is the way we want to do it. We call this, for our system, row echelon form. So our goal is to get our 3 variable system into row echelon form. Our solution, what this allows us to do is, we know that z equals 2. Then I can plug z equals 2 into this equation, figure out y, and plug y and z into the first equation and figure out x. So we call that process back substitution. We substitute just progressively into the other equations until we have all of our variables, the solutions for all of our variables. If we do that for this equation, we get that x equals -2, y equals 1, and we know that z equals 2. So our solution is an order triple. And we write it -2, 1, 2. So because we're using 3 variables, we end up with an order triple rather than an order pair like we had in a 2 variable system. Now on Friday we said we had, when we graphed 2 linear equations with x's and y's, we got lines. What are you going to guess, since we're in 3 dimensions now, that the graph of something like x minus y plus 2z equals 1 is going to get us? If we're adding a dimension. This turns out to be the equation of a plane. So when we have a linear equation, x, y's, and z's, like this, these are equations of planes. So what we're trying to figure out is where these planes intersect. And we'll talk about what that tells us a little bit towards the end. So our goal is to get our 3 variable system into row echelon form.
Can we talk to Simone?
Our goal is to get this 3 variable system into row echelon form, to find our solution, which is an order triple, and there are other possibilities we'll talk about in a second. The process we're going to use is called Gaussian elimination. So it's just a process of using the method of elimination that we use for 2 variable systems, but we have to do a little more work with 3 variable systems. Gaussian elimination, named after Carl Friedrich Gauss, who was a very famous mathematician and did work in physics also. Had one of the most famous mathematicians in kind of recent times. So we're going to use three basic rules to do Gaussian elimination. We're going to have our three variable system. Our first rule is we can switch the places of two equations. So if our system of equations was written in an order that we didn't like, we can change the order that our system of equations is written in. I don't have to write it in the order that they give it to us in. So we can switch the places. Our second rule that we're going to use, or second tool that we're going to use, is multiply any equation by a number. And we don't want to multiply by 0, because then that gets rid of the entire equation. So we can multiply any equation by a number, just like we did when we were solving two variable systems. We multiplied 1 by 2 and 1 by 3 and added them together, that kind of thing. And then the third step is what I just described. We can add one equation, I'm going to say to/from any other equation. So with a two variable system, it was pretty easy because we only had 2 to work with. Well, when we have 3 to work with, there's a little more we can do. So when we use this process, we use Gaussian elimination to get our system of equations into row echelon form, and then we use back substitution to find our solution. They call these steps, these 1, 2, and 3, they call them row operations. These are our row operations. And what we're going to do is, today we'll talk about this 3 variable system. Tomorrow we'll talk about an application that ends up with systems of equations. And then we're going to talk about how we can turn this into something that we can do with matrices. And I know some of us know a little bit about using matrices. I saw some of us did a matrix thing on the test, and we're going to talk about how we make that process just a little more robust, I guess you could say. All right, nothing complicated, nothing difficult, very mechanical, very repetitive, which is kind of nice. The downside is there are lots of places for arithmetic errors because we're doing arithmetic over and over again, or to get a sign, a plus or a minus, wrong. So we have to be a little bit careful, but it's a pretty mechanical, pretty repetitive process. So what I want to do is go through a couple of examples of doing these row operations to get our system of equations into row echelon form. All right, questions? All right, so let's do a couple of examples. So here's our system. X minus 3y plus 2z equals 1. 2x minus 5y plus z equals -5, and 3x plus y minus 2z equals -1. So there's our system. We want to use row operations to get it into row echelon form, so then we can use back substitution to solve. For this first one, we're going to go, I'll just do one step at a time, and we'll rewrite our system after each step. So the general procedure, we want to use the first 2 equations. Let me move this over. And I'm going to call this equation 1, equation 2, and equation 3, just to help us visualize what we're doing here. our general process, we want to use the first two equations to get rid of this x in the second equation. We want to use the first and third equation to get rid of the x in the third equation. So then we'll have two equations with no x's, and then we use the second and third equations to get rid of the y's. Generally what we're going to do. All right, so what do we have to do? Now, when we go through this, the first equation is not going to change. So our second, after our first step, we're still going to have that as our first equation. But we're going to do something with these two equations to get rid of that 2x. So what can we do with these two equations to get rid of that 2x? I want to multiply, kind of like what we did with a two-variable system, so I can add these two together and get rid of that 2x. We want to multiply, I'm going to write that in red, multiply 1 by negative 2 and add to number 2. So I'm going to multiply this one by negative 2 and add it to this one. So negative 2 times x, negative 2x plus 2x, I get no x's here. Negative 2 times negative 3 is positive 6 minus 5, I get a 1y. And then negative 2 here, I get a negative 4z plus 1z, so I get minus 3z. Multiply negative 2 here. Negative 2 minus 5 is negative 7. So that gets rid of that x in that first column. Now what can I do with the first and the third equations here to get rid of this 3x? Multiply by negative 3. And I'm going to add to 3. So when I add, I get a negative 3 plus 3. I get no x's there. Negative 3, so I get a positive 9 plus 1 is 10y. Here I get a negative 6 minus 2 is minus 8z. And a negative 3 minus 1 is negative 4. So that's my new system of equations. I've gotten rid of the x's in these two. Now all I have to use is, say, 1, 2, and 3. Now we just need to use these two to get rid of this y in the third equation. So what are we going to do? What are we going to do to get rid of this 10y here? Multiply 2 by negative 10. Add to 3. So I'm going to rewrite my system x minus 3y. The first two rows aren't going to change. They stay the same. I got rid of this x here, so I get y minus 3z again equals negative 7. Multiply this one by negative 10, so the y's go away. I get a 30 minus 8 is 22. And multiply this by negative 10, negative 70 minus 4 is 66. And now I have my system in row echelon form. Got rid of this x, got rid of this y, and now I just have a z in that equation. So from here, that's what we're going to do next. So from here we can say this tells us that z equals 3. Then I'm going to plug that into the next equation. So y minus 9 equals negative 7. So y equals 2. And then I'm going to plug in 3 for z and 2 for y in the first equation. I get x minus 6 plus 6 equals 1. So x equals 1. So my solution is 1, 2, 3. So that's our basic process. We start with our system of equations. We want to eliminate these two x's, and we want to eliminate that y. And we use our row operations repeatedly until we get our system of equations into this row echelon form. Exactly like we did with two variable systems. We just have to repeat the process a few more times here. Questions about what we did there? All right, let's look at another system of equations. So what this tells us is that these three planes would intersect in the single point, the point 1, 2, 3 in space. X, Y, Z, yes. So it goes in alphabetical order. Yeah. So we'll talk about that in just a second. All right, so let's look at another example of getting our three variable system into row echelon form. So here we have x plus 3y minus 2z equals 1, minus x minus 2y plus 6z equals negative 2, and 3x plus 11y plus 2z equals 6. And we want to solve this three variable system. So what's going to be our first step here? Let's label our equations 1, 2, 3. So what's going to be our first step? What's that? What? I'm sorry, one more time? We could do that. We could switch some places. But what's going to get rid of this x here? Just add 1 and 2. So I'm going to add 1 and 2. So my first equation is not going to change. X plus 3y minus 2z equals 1. I'm going to add these two together. Those go away. 3 minus 2 is 1, y. Negative 2 plus 6 is plus 4z, and add these two together equals negative 1. And what can we do to get rid of this 3x? Multiply the top by negative 3. Add to 3, and that'll get rid of this 3x. So negative 3 times x plus 3x, that goes away. I get a negative 9y plus 11y, which is 2y. And I get a 6z plus 2z is 8z. And I get a negative 3 plus 6 is 3. So after performing these two row operations, let me move this down because we did it to the second, we place the second row. Plus 2. so now we got rid of the x's here. Now all we need to do is get rid of this 2y here. So what are we going to do to this set of equations? 1, 2, and 3 to get rid of that 2y. Okay? So we were multiplying this one by negative 3, so this would be a positive 6z plus 2z. Okay. But that's definitely the kind of mistake that's easy to make in here, is just missing a negative sign. So what are we going to do to get rid of this 2y with these two equations? So what would be our process? Okay, so let's see what happens. Multiply 2 by negative 2. Add to 3. So I get, for my system, x plus 3y minus 2z. That doesn't change. We'll keep this one. Y plus 4z equals negative 1. I get a negative 2y plus 2y, I get no y's. I get a negative 8z plus 8z, I get 0. And I get a positive, did I make a mistake here somewhere? 3. Oh, so I get 6 minus 1, I get 5. 0 equals 5 on that last row. What does that tell us? No solution. So that tells us these three planes are parallel. So if we get no solution for our 3-variable system, it tells us our 3 planes are parallel. So anytime you get something like this where 0 equals 5, 1 equals 2, something like that, we're going to get a no solution. Yes?
Is this assuming the planes to be like infinite though? Because the plane is certain.
Yeah, the planes are infinite.
Does that mean that they're all parallel or just
So that's the other piece that I want to talk about in just a second. So I'll talk about it in just a second. So we can have 3 parallel planes or something else. And we'll talk about what the something else is. All we have to say is no solution. There's no solution. And we'll talk about what the something else is in just a second. If you come up with something like 1 equals 1, or 0 equals 0, or 2 equals 2, we said on Friday that gives us an infinite number of solutions. And we said with the 2-variable system, we ended up that our 2 lines were the same. Well, if we get an infinite number of solutions with 3 planes, that means the 3 planes are intersecting in a line. So we get an infinite number of solutions, that means our 3 planes are intersecting in a line. We're not going to have to write what that line, the equation of that line, the equation of line in space is just a little more complicated than the equation of line in a plane. We've actually been talking about that in my calculus class, working with planes or with planes and lines in 3 dimensions. All right, so our process, just to backtrack, our process is to, in general, use the first 2 equations to eliminate this x. Use the first and the third equations to eliminate this x, and then whatever's left, We use the second and third equation to eliminate the third y, so we get our system in row echelon form, and then use back substitution. So let's take a look at our possibilities when planes intersect. Pull this up. Close this. All right. So the ones we've talked about so far, when we get one solution, our three planes are intersecting in a point. So that would be this point right here where the three planes come together. They don't have to come together necessarily at 90-degree angles, but three planes would intersect at this point. When we get an infinite number of solutions, our three planes are intersecting in a line. So anywhere along that line, extending forever in either direction, would be a solution. And then our no solution possibility, we could have all three planes parallel. We could have two planes parallel and they intersect. One plane intersects both of those. We could have three planes intersecting, each intersecting in two lines with another plane. So these would all be no solution. These would all be no solution cases. And you have to do a little more work to figure out what possibility you have there. All we have to say is no solution. What's that?
How do you know we come across ones that parallel to
Well, to find parallel planes, you would be able to, you know your planes are parallel when you end up with something like 3x plus 5y minus 2z equals 11, and 3x plus 5y minus 2z equals 15. Those two planes would be parallel. So you'd be able to reduce two of your equations to something that where all the coefficients were exactly the same and they just differed here. So you know that those two were parallel. And then you could figure out where the other plane, how the other plane intersected those two. So that would be the process that we would use. And then for the other case, you'd have to see, do the two planes intersect, and then where do those two planes intersect the third? So that one takes a fair amount of work. So just a little extension there on visualizing 3 dimensions. But any questions on our process here? Getting our system into row echelon form. Exactly the process we use with two variable systems. We just have to do it repeatedly. Very, very mechanical, very repetitive, but not difficult. Okay. Let me ask you one quick question before I give you your homework. What if we had a 3 variable system? And I'm going to steal one of these. And something like what if we had a 3 variable system but only 2 equations? What would our solution? What would our possible solutions be here? Just kind of a thought experiment. So what are these two? What do these two represent? They each represent a plane. So what are our possibilities for planes? They could intersect in a line, or they could be parallel. So these two are either going to be parallel or going to intersect in a line. So 2 planes are always going to be either parallel or intersect in a line. Just wanted to get you thinking about that a little bit. All right, homework. And just to tie this in with what we've been talking about before I give you your homework, we can use the dot product to figure out the angle between those 2 planes if they're not parallel. So we can figure out vectors that are associated with these 2 planes and use the dot product to figure out the angle between them, just like we figured out the dot product between, or the angle between 2 vectors. So to tie 3-dimensional stuff with what we've just been doing. Homework, page 499. Yeah, the dash was easier to write than a 2, Joanne. The dash was easier to write than a 2. All right, there we go.